Hi, welcome to my channel. In the previous video, we discussed about the what is MNST dataset, what is MNST dataset, and training a binary classifier, training a binary classifier, and performing the then measuring the accuracy using the measuring accuracy using the accuracy using cross validation, and also we are finding the kind of different types of performance metrics based on the confused matrix, and like precision recall, F1 score, precision recall, trade-off, and and also we are finding out the ROC AUC curve. Okay, AUC curve of the binary class classification problem. Okay, now, and also we are finding out the what is meaning of multi-class classification problem. And also classification problem. Okay, and also we discussed about the what are different performance metrics for the multi-class classification model. And in this video, we are going to see the what is meaning of error analysis. We are going to avoid the error analysis in this video. Okay, so now what is meaning of error analysis? Okay, if this were a real project, you now follow the steps in your machine learning project checklist. Okay, then you would explore the data preparation options, and also you try to find out the multiple models, shortlisting the best ones, and fine tuning their hyperparameters using the grad sets, cross validation, and automate such as much as possible. Like that, we are going to find out the different steps. So we are going to do one project. First of all, you have to find out the data preparation, then apply select the best different models. Okay, among all the models, we have to find out the best model. For that model, we are going to find out the fine tune all the hyperparameters. So this is the procedure we have to follow in the error analysis. Okay. Now we are going to assume that okay, if you found a promising model, that means best model, and you would want to find the just you want to improve that. Okay, improve that. So one way is to do analyze the types of errors it makes. First of all, you have to identify what are different types of errors in the corresponding model. Okay. So here, first of all, you are looking into some example with help of our MNST dataset. It contains 70,000 handwritten images. This is divided into two parts, training and testing. So the training contains 60,000 images and testing contains 10,000 handwritten images. So the class labels are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. These are the different types of handwritten digits. Okay, now we are going to construct the after training a model, we are going to construct the confusion matrix to find out the performance of this model. Okay, so now we are going to use the prediction of using the cross underscore val underscore prediction function, then call the confusion matrix. It displays all the values of all the actual values, and it displays one matrix called as a confusion matrix. It contains the rows contains actual values, the rows called as a actual values, and the column called as the predicted values. Okay, so here the row indexes start with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the index of the corresponding rows. These are the digit 0, digit 1, digit 2, digit 3, digit 4, digit 5, digit 6, digit 7, digit 8, digit 9. Like that, we are going to find out things, the actual values. So in the column wise, we are going to have the 0 in digit, 1 digit, 2 digit, 3 digit, 4 digit, 5 digit, 6 digit, 7 digit, 8 digit, and 9 digit. Okay. For example, here, we are seeing that the index, the image, digit images, our input given image is actual input image is 5. This is called actual image. Okay. For the actual image, for example, okay, here 4,400 images correct. These are the rows, or this is the row. Okay, this is the row. Okay, these are the actual row data, actual 5 day. Okay, and but what happened? The actual 5 images predicted as a 26 times as a 0, 26 times as a 0, and the actual 5 digit is predict as a 16 times as a 1, and the actual 5 digit is predict as a 31 times as a 2, and the actual 5 digit is predict as a 3 times as a 173 times as a 3 digit. So like that, here the actual 5 digit image predict as a 5 predict as a 5. Okay, predict as a 5 like 4,484 times. Okay, so like that, this is the way we are going to find out the construct the confused matrix. Confused matrix is the what is the actual values of the how many times are they, that is the predicted values. Okay, so in order to construct this one, we are going to use the code. Okay, so class underscore val underscore predict, our mode is stochastic gradient classified, x underscore train underscore square value. Okay, y underscore train value, and class value is equal to 3, and for that we are going to use we are storing that value in the y underscore predicted values. These are the predicted values of our model. So we are using the scaled version. That is, in the previous video, we are constructed, we have transformed all the features of the x into standard scale. Okay. Now we are going to based on the actual values and the predicted values. So it will construct the confused matrix. Confused matrix y underscore and comma y underscore train underscore predicted value. These are predicted values and these are the actual values. So for that, we are going to display the confused matrix. The confused matrix contains the actual values versus predicted values. Okay, now it's very the confused matrix contains a lot of numbers, so it's very difficult to understand what is the things. Now we're going to convert that confused matrix in the form of one image representation. Okay, that means we're going to convert the image representation of the confused matrix with the help of some code. Okay, using the matplotlib mats show function. Okay, so plot.mats show confused matrix. For the confused matrix, we are going to convert that into image. Okay, cmap equal to plot.color map.grayscale image. So plot.show, that this whatever the data is here in the confused matrix, that is converted in the form of images. Okay. Now the confused matrix look good at pretty good, but the most images are in the main diagonal values. Okay, since the most images are on the main diagonal values, so here the some values are there. Some values are there. So here all the it is between the 0 to some grayscale images are there, and the remaining things are maximum are black and white, black only. Okay, now, so which means that they are very classified correctly. So the files, the index value 5, the index value 5 somewhat good, somewhat slightly darker than the other digits. Okay, now which could mean that there are fewer images of files in the data sets. The data set are the classifier does not perform as well as files on the other classes, other digits. Okay, in fact, you can verify the both are the cases. Now let's focus on the plot on the other errors. So first of all, in order to find out the errors in the model can be in the image, first of all you need to divide the each value in the confused matrix by the total number of images in the corresponding classes. That means, for example, here uh, so here the number of images here, for example here, okay, the total number of you have to find out the total number of uh, elements in the corresponding row divided by so here 5578 by the total number of elements in the corresponding row. So that is suppose 5578 plus 22, okay, 7 8, like that we will find out the sum of all the row elements by that must be divided by the corresponding elements. So that gives the error. Okay. So now, so that means you divide the each value in the confusion matrix by the number of images in the corresponding class. So that we can compare the error rates instead of absolute number of errors. Okay now. So like that we are going to find out the error rate. What is meaning of the error rate? Here we are going to divide the each value in the confusion matrix. Okay, suppose this is a zero index value. It contains some rows are there. Okay, you will find out the, so suppose you will find out the error of this image, okay, this value. So that gives the, so this is called A. So A by error at A by the total number of elements in the corresponding row. Suppose A, B, C, D, E, F. That means A plus B plus C plus D plus, okay, E plus F, like that. Okay, that is the number of images in the corresponding cell by total number of images in the corresponding entire row. That gives the error rate. Okay. So row underscore sums equal to confusion underscore max dot sum. Okay, x is equal to 1. Keep dimensions equal to true, and normalization of confusion matrix equal to confusion matrix by confusion matrix value by row sums. So here we are going to find out the two different types of confusion matrices here. So fill the diagonal value with zeros to keep only the errors. So here in the transformed output, it get the all the diagonal values into 0, all the diagonal into zeros, and plot the results. So here np dot fill underscore diagonal normalization of quotient matrix confusion matrix equal to 0, plot dot math show normalization of confusion matrix max, okay, comma confusion matrix of color map equal to plot dot cm dot gray. So plot dot show, that shows the two different types of graphs. So here this is the actual your converted confusion matrix converted into image file format. Then this file converted into all the diagram values converted into zeros. Now this is the representation of the two figures. This is the converted confusion matrix converted into image file format. Okay, here all the diagonal values give the your accuracies. Okay, accuracies. It contains some image values, but it is converted into the form of all the diagonal values are converted into 0. Okay. Now you can clearly see that the kinds of errors in the classifiers. Okay. Now remember that there are rows represent the actual values. Here we are going to know these are called as actual values, and these are called as predicted values. These are the rows called as actual values, and these are called as predicted values. Now, while column represents the predicted values, the columns of class A is quite bright value. So here the column, after converting the error analysis by using you are converting into error analysis like dividing the corresponding class label by the total number of elements in the corresponding row. Then we are getting the error analysis. After converting that one, the class label, the column label 8 gives the some bright values, which is mainly that many images are in this region are going to be misclassified as 8. So that is the major finding of the converting the error, converting the image into confusion matrix into image format. Okay now. So now, however, the rows for the class A is not that bad. So the rows, so that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The rows are not bad. Okay, the rows are not bad. But whereas coming to the class label, the corresponding column, okay, column 8. This is column 8. But it is the column shows the bad classification. Okay, as we see that the converged matrix is not necessarily a symmetrical format, and we can also see that that classes 3, the classes 3 and the classes 5, class 5, okay, often get the confused. Okay, often get the confused at the class level 3, okay, class level 0, 1, 2, 3, 4, 5, 6, 7, 8. By seeing this converged matrix, the class level 5 and the class level 3 are getting sometimes are getting the confusion, and the remaining things are very normally you will get the there is no confusion. Okay, now. So now analyzing the convergent matrix, okay, often gives the insight into ways to improve your classifier. Okay, so now looking at this plot, it seems that your efforts should be spent on the reducing the false 8. Are going to split false 8. Okay, more number of elements are classified as a 8. Okay, so for example, you could try to gather more training data for digit that look like a 8. Okay, so that the classifier can learn the distinguish between them for the real 8s. This is one way. Or we could engineer the new features that help the classifier. For example, writing an algorithm to count the number of closed loops. Example, 8 has 2 and 6 has 1 and 5 has none. Okay, or okay, you could pre-process the images. You could pre-process the images. Example, using the scikit-learn image, pillow or OpenCV. Okay, to make some patterns as the closed loop standard out mode. Okay, analyzing the individual errors, you can also be a good gain insights on the what your classifier is doing and why is failing, and but it is more difficult and time consuming. Okay, for example, let's plot the example of 3s and 5s. 3s and 5s. We are having the 3 digits and 5 handed digit 5. The plot underscore digit function just uses the matplotlib image of function. With that, we are going to draw the differences between the class A and class 3 and class B, class 5. So here the class label A equal to 3 and class B equal to 5. So we are going to define the four things are there. First thing is x underscore A. That means x underscore train A train that contains the y underscore train equal to class label A. That means 3, and y underscore train underscore prediction also class label A. That means both are training and the prediction actual class level is 3 and predict class also with 3. So both are the same. Okay, and x underscore A and A B equal to x underscore train y underscore train equal to class A, that is equal to 3, and y underscore predictive value equal to class label B, that is equal to 5. That means their combination of 3 comma 3 is one figure, and 3 comma 5, that is the actual value is 3 and predicted value is 3. Actual class level 3 and predicted class level is 5. And x underscore BA equal to x underscore train. Okay, the input value train equal to class level B. That means here we are giving the input as a training as a class level as a 5, and class level we are predicted class level as a 3, class A, that is 3. Okay, that means 5 comma 3. And class label x underscore b equal to x underscore train y underscore train equal to class label p, that is equal to 5, and y underscore train underscore predict equal to class label equal to b, that is equal to 5. That means 5 comma 5, 5 comma 5. That means actual value is 5, predict also 5. Sorry, 3. Actual value is 5 and predict also 5. So like we are going to find out things. Now we are going to draw the graph between all the four possibilities. So this is the output of this graph. This is the graph. Okay. So it shows all the elements are the actual class label is 3 and predict also 3. And this is the graph between the actual class label is 3 and predict as a 5. Okay. And this is between the actual class label is 5 and predict also 5. And this is the class between the The actual class label is 3, 5, and predicted also 5. Like that, we are going to draw the different graphs within graphs. Okay, this is the output of this one. Now, the two 5 by 5 blocks on the top 5. Okay, top this is classified as a 3. So this is the 3. All these are classified as exactly 3. And the two 5 by blocks on the bottom shows the classified as a 5. Okay, this is nothing but classified as a 5. Sorry, classified as 3, and this is classified as a 5. This is classified as a 5. Now, some digit that classified gets wrong in the, that is bottom left and the top right blocks, so are badly written that even a human would have trouble classifying them. Example, 5 in the first row and second column truly looks like a badly written 3. However, most misclassified images seems like a obvious errors to us, and it's hard to understand why the classifier made the mistakes he did. Okay, the reason is that we use the simple stochastic gradient classifier, which is a linear model. Because of this one, we are going to misclassify the class label 3 as a class label 5 and class label 5 as a class label 3. So because of the simple model, that is a stochastic gradient classifier. Okay, all it does the assign a weight for the each and every class to the pixel class. Okay, and it sees a new image. It jumps the sums of the weighted pixels intensities to get the score for each class. Okay, so since 3s and 5s are differ only pixels only, that's why we are going to mismatch the things. This model will easily confuse them because of the less number of pixels. Okay, so the main difference between the 3s and 5s is the position of the small lines. The position of the small line, that is 3 and 5, both are small. Okay, because of the small regions. Okay, because of the small region. Okay, that joins the top line to the bottom arc. Okay, so if you draw a 3, with the junction slightly shifted to left, okay, then the classifier might classify it as a 5 and vice versa. Okay, so because of small difference, okay, now that's why it will get the misclassified. So in other words, this classifier is quite sensitive to the image shifting and rotation. Because of this one, we are going to misclassify the class label 3 as a 5 and 5 as a 3. So one way to reduce the 3 by 5 confusion is would be to pre-process the image to ensure that they will well centered and not too rotated. This will probably help the reduce the other errors as well. So in the like that, we are going to analyze the things. Okay, analyze the errors of the current by using the confusing matrix. Okay, now in the next video, we are going to see the multi-label classification. Thank you for watching our video. Please subscribe to my channel. Thank you.